All right, everybody. Welcome to my latest office hours. Hopefully this time I've done a little bit of digging to resolve some of the technical issues that I've been experiencing in the last couple of episodes, I guess we can call them now. Hopefully that's resolved. Let me know if it isn't, but already it's starting to look a little bit better. So fingers crossed this holds. Long story short, it wasn't a bandwidth issue, but it looks like it was an encoder issue, so software rather than bandwidth. Easier to fix, so I guess that's the better of the two options. Alright, well, welcome everybody. Today's office hours don't have a very specific set agenda. As I mentioned in the invitation to everybody, this is more of an Ask Me Anything type event. Broadly focused on recent events in the Earth and climate system, meaning the long and remarkable sequence of continental scale extreme to record-breaking heat waves this summer. Similarly extreme, perhaps even more so, marine heat waves in different ocean basins around the world. Pretty wild things happening with wildfire, particularly in Canada this year. The western U.S. notably slow start to the wildfire season, but that may be rapidly changing over the past week or so as conditions have been record warm. And then we can talk potentially about California as well. This year has been a weird year, and it is one of the only locales in the entire world, in fact, that has been until recently near or below average temperature-wise, and in some cases California, parts of coastal California have been well below average, or at least well below the recent 30 to 50 year average temperature so far this season. That has changed in July. Now many places in the Central Valley and in the interior deserts of California are actually in the running for the top 10 or even top 5 hottest Julys on record, so that's quite a change of pace, although along the immediate coast, this July has continued to be a relatively modest month, and so places in between, your mileage may vary, but in general, so far this season in California, it's been weird. Cool start, much hotter recently though, anomalously hot. Certainly a wet start, as we've talked about before. That has delayed fire season, especially at higher elevations, will likely continue to do so in California at the highest elevations throughout the season, but conditions at lower to middle elevations have drastically dried out with the record-breaking heat waves in recent days, and so fire season there is now really getting going, finally, a little bit late, but will probably still peak later in the season, as is typical, where the flammability at lower elevations rises from early summer into late summer, and then even potentially peaking in early autumn, so there's still some time to go there as we head into offshore wind season. So again, my monologue today is going to be pretty short. That's just about it. What I really wanted to do was solicit a wide range of questions today centered on any of those things, or I suppose if we have time, other things as well. El Niño, climate change broadly, a fairly open hour today. I would like to keep the focus mainly on what's been happening recently in the climate system, but I think depending on attendance today, I'll be able to take some other questions as well. I will note that it does seem like the video and audio are syncing much better, so I think that likely confirms it was indeed a software rather than a bandwidth issue, so that's good news. One other thing I mentioned is that you can still pre-order that extreme weather and climate calendar that I've been working on through August, and then I guess after that point you can order it via regular means. And there will also be at least 1 year of follow-up. We just completed the draft at Workman Publishing for the 2025 Extreme Weather and Climate Calendar, which includes a lot of new material that folks might find interesting. So if I do things right, I'll embed a link in the recorded version of this video right around here where I'm talking about it. Alright, so there aren't too many questions in terms of the live chat, which is interesting given that this is explicitly an Ask Me Anything day, so take advantage of it. And it looks like I spoke too soon. Looks like there's a bit of a lag there, but hopefully it's minimized, and I'll still continue to work on it. There are a couple of questions, and so I'll start with them now. There's the first one's from Eric, which is, how is El Nino developing in the Western Pacific? Well, I will note that El Nino and its cool counterpart La Nina are primarily defined by changes in the eastern equatorial Pacific Ocean rather than the west. There are changes in the west that occur as well, but El Nino fundamentally is defined by anomalously warm temperatures in the eastern tropical Pacific Ocean, so just off the coast of Peru and some adjacent countries there. And there we've been seeing astonishingly warm temperatures from that so-called El Nino costero. And temperatures along the coast there at times have been anywhere from 5 to 10 degrees centigrade, so in some cases in excess of 10 or 12 degrees Fahrenheit above average. Those are huge ocean temperatures anomalies in the far eastern tropical Pacific Ocean that have brought major impacts locally in Peru. It is, of course, much warmer and more humid than usual there, but also some of the desert regions that rarely see heavy rainfall have seen quite extreme downpours, as is typically the case during such events. The reason why you can see such dramatic warming there, it's usually very hard to warm oceans by that much, because just think about how much energy it takes to heat a pot of water to a boil. Even that, a couple of liters of water, it takes a tremendous amount of energy in the form of a flame in direct contact with that pot for a sustained period of time to bring up the temperature significantly. So when you talk about a 5 or 10 degrees centigrade increase in ocean temperatures over any region, just imagine the volumes that we're talking about. Even if that's a shallow layer of water, just a few meters deep, that's still an enormous amount of energy required. And the reason why you can get so much warming in what is often referred to as the cool tongue in the tropical eastern Pacific Ocean is precisely, the name sort of gives it away. It's because it's an anomalously cool region to begin with, because you have upwelling of cool water from beneath. So the water in the equatorial Pacific Ocean in the far eastern part of the basin is almost artificially cool, and I use artificially somewhat generously because it's not artificial, it's a natural process. The upwelling is the consequence of oceanographic and climatological processes, of course, but what I mean is, if that localized upwelling weren't present, the ocean there would be much, much warmer. And so, rather than the atmosphere sort of top-down heating the surface of the ocean, in this case, what's really going on primarily, and there is some contribution from the atmosphere heating the ocean, but it's a secondary at best process. The primary thing that's going on is that vertical motion, that upwelling of cool water from beneath gets severely attenuated during an El Nino event in the eastern tropical Pacific Ocean. So it's not so much that you're actively heating the surface layer directly, it's that you've stopped the active cooling from occurring. And it turns out that it's much easier to do that to warm the surface in this part of the world, because you don't actually have to add huge amounts of additional energy from the atmosphere to the ocean, and it's hard to do that transfer. Air to water heat transfer doesn't happen that quickly or that easily. Instead, what you really do is you just remove the cold water supply from beneath, and that warm water sort of accumulates near the surface. And that's because you have essentially a weakening, or occasionally even a reversal, of those easterly, so east to west blowing trade winds that induce this circulation vertically in the ocean to begin with. So we have been seeing that this year in the far eastern equatorial Pacific Ocean in spades. It's extremely warm near the coast of Peru. And we have seen significant warming in the sort of the canonical, it's called the Niño 3.4 region, which is really just a box drawn, a rectangular box, elongated in the longitudinal sense, in the tropical Pacific Ocean, that is thought to be the most important region for understanding El Nino. There's some debate about that, but it has historically been the traditional way to define El Nino and La Nina. Find the temperature anomaly in a box, and if you exceed certain thresholds on the warm side, it's El Nino, and certain thresholds on the cool side, it's La Nina. This year we've been hovering right around the El Nino threshold in that box for a while. It's kind of stalled out recently. It's still much warmer than usual, but hasn't warmed further in recent days, even though the eastern tropical Pacific Ocean, east of that Niño 3.4 box, is far warmer than average, and it greatly eclipses the Niño 3.4 box. So right now, we have a warming in the Niño 3.4 box that's right on the cusp of officially declaring an El Nino. It's probably enough if it's sustained for another month. But it kind of undersells the situation, of course, because east of that box, things are much, much more anomalously warm than they are in the canonical El Nino box. So it's really an eastern tropical Pacific question rather than a western tropical Pacific question. There is a bit of a dipole during many El Nino events. The western Pacific Ocean is a bit cooler than it would be otherwise, because you have that sloshing effect of the warm water volume in the west sloshing eastward, and you have some inhibition of those easterly trade winds that help pile up that warm water in the west. That has been interrupted a bit by climate change now, that the western tropical Pacific has just been warm almost all the time now, so it kind of varies from extremely warm to very warm, depending on El Nino versus La Nina, instead of warm versus cool, as it used to. So that's an interesting point of research, actually, how that might affect large-scale El Nino teleconnections, because what matters most in terms of how El Nino affects regional climate, in terms of hydroclimate, so how much rain California and the Southwest receives or doesn't receive, whether there are severe droughts or floods in East and Southern Africa, or in any number of other regions around the world. And El Nino is famous for producing those effects, where it has, in some cases, larger effects thousands of miles away from where the phenomenon is actually defined in the eastern tropical Pacific Ocean, versus where it has the greatest influence, sometimes thousands of miles away, through indirect atmospheric effects known as teleconnections. It's really the spatial pattern of anomalous ocean temperatures that appear to matter the most. In other words, it's not the absolute magnitude of how much it's warmed, but it's how much certain patches of the ocean warm relative to other patches of the ocean. So if you can imagine, as a thought experiment, if the threshold for declaring an El Nino event is, say, the Niño 3.4 box has got to be warmer than half a degree centigrade above average for at least 3 consecutive months, well, okay, imagine a world in which the entire global ocean artificially warmed by exactly 0.5 degrees centigrade. By the traditional definition, you'd have an El Nino event, because that piece of ocean would be sustainably warmer than average for a few months. But would you have the typical El Nino effects? Probably not, because everywhere else also warmed by 0.5 degrees centigrade. And so the gradients, the spatial differences, if you will, across the ocean would actually not have changed despite all parts of the ocean warming. So that's an idealized, exaggerated example, of course, but that's not dissimilar from what's happening in a warming world, where in general, really nearly all of the global oceans are warming significantly, but that warming is occurring more rapidly in some places than others. And so, on the one hand, when the Niño 3.4 region is a degree centigrade above average, that's not as much of a departure relative to the global average ocean temperature as it used to be when the global oceans were cooler. On the other hand, because the global oceans are not warming uniformly everywhere, that further complicates the situation, because what we're really seeing, especially this year, are patches of extreme and really genuinely extraordinary and record-breaking oceanic warmth in some regions, and relatively ho-hum terms, there's definitely way more extremely warm and record warm oceans. It's just that some regions haven't warmed all that much at all. And I'm noticing one more piece of lag here, and so since I know what I think is going on, I'm just going to adjust this setting on the fly, so bear with me just for a moment here as I deliberately degrade the encoding quality slightly further, and hopefully that completely eliminates the lag at this point. So really what we have is a situation where the global warming plus natural variability that's not El Nino plus the natural variability that is encompassed within El Nino are all interacting in ways that are really complex. And so right now, and this relates to another question that just came in about why are global ocean temperatures so extremely warm, it's a confluence of factors. So why is the tropical Pacific Ocean off the coast of Peru extremely warm? Well, that's pretty much El Nino, and a strong El Nino costero at that. So El Nino can explain some of the anomalous global warmth, particularly in the tropics and in a couple of patches elsewhere in the mid-latitudes. But as some other climatologists have recently pointed out, the typical El Nino response in terms of global temperature is, of course, to make the planet warmer overall, but it doesn't make all regions warmer. In fact, that anomalous warmth during and immediately following El Nino events and the global average is strongly concentrated in the tropics. The mid-latitudes, some places, tend to be cooler than they otherwise would be in El Nino years. So that's why it's so striking that this year, not only do we have record-breaking warmth in the tropics, part of which is very likely associated with El Nino, but we also have record-breaking warmth in places that El Nino probably should be making cooler than average in the summer months, and yet they're experiencing. We really can't invoke El Nino to explain all of this. And of course, the overriding factor in why the world is as warm as it is right now is human-caused climate change. Because I cut out there. Okay, I'm still having some issues, so I'm going to have to dig into this further. If anybody has streaming advice as to why this might be happening, please feel free to reach out to me afterward. Just to be crystal clear on that point, the main thing that's going on is climate change. Why is the Earth reaching all-time, or at least all observed time record temperatures this year, both on the land and at sea? Well, that is because of human-caused climate change. Why is this year significantly warmer than, say, the last couple of years, though? That's still, I think, on a global mean basis, we can invoke El Nino to explain a decent chunk of why is this year warmer than last year or the year before. But would we be experiencing record-breaking warmth if we had no climate change and just an El Nino of this magnitude? Absolutely not. We wouldn't be anywhere near as warm as we are, and most of the places that are breaking all-time temperature records would not be doing so. So what's the most important factor? Probably climate change. El Nino is important regionally and in terms of stair-stepping, as I talked about last time, above our antecedent records. But in general, it's, why are we as warm as we are? It's because the whole planet is warmer than it used to be by a considerable margin because of the continued accumulation of heat-trapping greenhouse gases in the atmosphere. But the regional question of why there are certain patches of ocean that are so extremely warm right now is interesting. As I explained, the eastern tropical Pacific Ocean, that's fairly easy. It's mostly El Nino in all likelihood. But some of the extratropical, so the non-tropical oceans that are extremely warm right now, and there are two regions in particular of note, or I guess three. One is the one that's been talked about least in the news. There's an extremely warm water, the blob, returned, if you will, off the coast of western North America in the northeastern Pacific Ocean. Folks along the California coast might not know it because it's actually been unusually cool along the coast of California. So the water temperatures along the immediate coast remain below average, but you go just a couple hundred miles offshore and it couldn't be more different. Temperatures are 3 to 5, even more centigrade, so in some cases locally 5 to 10 degrees Fahrenheit, again, above average. That's extremely warm. That's one region. The other region is the North Atlantic Ocean, which has been discussed much on social media and in the news. The region of the North Atlantic that is most anomalously warm has shifted a bit from the northeastern Atlantic, so off the west coast of Europe and northern Africa, now has shifted westward to the east coast of North America. So Newfoundland and Labrador in Canada are surrounded by extraordinarily warm water on the north side of the Gulf Stream. Again, 5 to 10 degrees centigrade warmer than average. These are very large anomalies. And each of these regions has essentially been affected by persistent or unusually persistent and strong high-pressure systems this summer that have remained stuck in place in those upstream of those regions or near those regions in such a way to favor patches of extreme oceanic warmth repeatedly. And the reason why that happens is the primary reason is that when you have a persistent region of high pressure over or near or adjacent to an ocean basin, you do two things. Typically, you inhibit the formation or the passage of storms, which from an oceanic perspective is perhaps most important because it inhibits vertical mixing. So that cold water upwelling I was mentioning, imagine when you have a lot of wave action and the water is churning, while the water, a couple feet below the surface is quite a bit cooler than right at the surface, directly exposed to the sun. So when you mix that up, you decrease the average temperature of the surface layer of the water. But when you have calm weather and light winds, glassy ocean surface, you're not really getting much mixing of the ocean, vertically speaking, and so under those light wind conditions, whatever sunlight does reach the surface layer of the ocean tends to accumulate heat there, and so the surface ocean can warm quickly. That's compounded by the fact that under high pressure systems, typically, you also have more sunlight than usual because you've inhibited the clouds and the storms and the precipitation, so you have more sunlight potentially warming the surface, and you have less wave action to mix warmth from the surface back with the waters beneath. And further, you tend to have, in many cases during summer high pressure systems, warmer than average air temperatures as well. That is, ironically, probably the least important part of this, but it does, after a few weeks, it does start to add up. So that's one of the main reasons why we see these persistent regions of warm water develop adjacent to or near persistent high pressure systems in summer over ocean basins, and that's in fact what we've seen, I think, over portions of the fact that there's been an anomalous level of Saharan dust blowing from North Africa across the central North Atlantic Ocean. This doesn't explain what's happening, though, up by Labrador and Newfoundland so much. The third region of extremely warm ocean, really there probably are others, but these are the ones that have been in the news, is the Mediterranean Sea, which is extraordinarily warm, really genuinely, shockingly warm. That has been supporting both extreme severe convective weather, so tornadic activity and giant hail in the northern Mediterranean, so in Italy, all the way up through Central Europe and Greece, where all that met across the region. That has been contributing to unusually severe weather in that context, as well as record-breaking heat waves and wildfires. So this is sort of that two sides of that hydrologic coin you keep talking about. Extreme anomalous warmth in the ocean and atmosphere can foster both extremely significant precipitation anomalies if there are storms around to utilize that moisture, but in the absence of precipitation generating processes, what it really does is suck more and more moisture out of the landscape if it's really, really warm because of that increasing saturation vapor pressure deficit, that increasing thirstiness of the atmosphere. And what in fact we have been seeing are that in regions that have not seen the extreme rainfall, and even in a few that have briefly seen that extreme rainfall, we've been seeing historically severe wildfire season in parts of Greece and adjacent countries. We've seen even on some of the Greek islands in the Mediterranean, some of the touristic sites. There have been some dramatic footage of people sort of running from their hotels down to the beach and getting on fishing boats because these fires have swept all the way from the mountains to the coast and burned right up to the ocean's edge. So dramatic scenes there, again, amid record warmth in the ocean, record warmth in the atmosphere in that part of the world. And here again, in the Mediterranean, it's a closed ocean basin, a sea. So the mechanisms are slightly different, but really not that different in the sense that persistent high pressure, not unusually calm conditions for much of the past couple months over the ocean, unusually warm surface temperatures, and because the Mediterranean is a closed basin with less organized storm activity, it is perhaps a little bit even easier for these high pressure systems to sort of amplify the warmth of the surface ocean, because there is overall a little bit less vertical mixing than there is in the larger open oceans basins in the world. So there are sort of diverse mechanisms, but there's some similarities. You've been seeing a lot of persistent and stagnant high pressure systems all throughout the northern hemisphere this summer. Work continues on exactly why that's happening, but there is an emerging literature suggesting that at least in summer, and at least in the northern hemisphere, that the configuration of the jet stream, the strength and the positioning of the subpolar and the subtropical portions of that split jet stream in the summer months in the northern hemisphere may increasingly favor these persistent or stuck weather patterns, again, during the warm season in the northern hemisphere specifically. And if, that would be consistent with what we were seeing this year, with what we've seen in recent years. And if that's true, it's potentially a mechanism by which northern hemisphere summer heat waves and also extreme precipitation events, because if there's a persistent weather pattern, if you're stuck under the ridge, it's record warm, but if you're stuck under the trough, you're actually going to get the opposite kind of pattern that may amplify both heat extremes and precipitation extremes in northern hemisphere summer, even beyond what you might otherwise expect from the more straightforward thermodynamic effects of global warming. So this would be an effect that adds to that in some regions. And the effects may vary, by the way, from one region to the next. It kind of depends exactly where the persistent ridges or troughs set up in any given year. And in California, we've seen different iterations of that. This year, California has not necessarily been persistently under the ridge, unlike in some recent summers. That's changed a bit recently, but in this case, it's Western and Central and Southern Europe have really been under the gun for a lot of this, as well as the Southern and Central U.S., where there has just been an unrelenting humid heat wave in some parts of the Gulf Coast states for months now. Miami is seeing heat indices above 100 degrees essentially every day, and that's not that's unusual. In fact, I believe Brian McNulty on Twitter or whatever it's called now, I believe as of this morning, X, pointed out that Miami, at least at the official observing site, has exceeded its daily record heat index for most of the past 30 or 40 days, like every day. That is a pretty extraordinary feat in a place that's already quite hot and humid to begin with. So Phoenix, not nearly as humid as Miami, of course, but more humid during the monsoon season than I think folks from outside of the region sometimes realize, has been above 110 degrees, at least briefly, every day for weeks now. Set a new record for consecutive 110 degree days, and has seen a couple of days up nearly at 120 degrees, 118, 119 degree days, which even by Phoenix standards is extremely hot and record-breakingly hot, at least in terms of daily records. To which a lot of folks say, I've been in Phoenix when it's been 125 degrees, and the answer is, well, your car thermometer, the bank thermometer, might have read 125 degrees, I'll believe that, but those are not accurate or reliable measures of temperature. Those are measuring the temperature of the air immediately off the surface of your extremely hot car hood or the bank roof. When people say it was such and such temperature in the shade, well, that's actually how you're supposed to measure temperature. Official weather sites and observing platforms actually, essentially, you put a thermometer inside a shaded and ventilated box so that it does not get directly exposed to the sun. Because if it is directly exposed to the sun, largely what you're measuring is a blend of the actual air temperature and the temperature of the hot surface of the thermometer because of direct solar radiation that's incident upon it. So you actually want to shield thermometers from direct sunlight if you want to get a number temperature-wise that's comparable or for an apples-to-apples comparison with official weather records. This is a perennial problem with weather station siting, and if you build too enclosed of a box, of course, that will heat up still like a hot car, so you need both to shade the thermometer and keep airflow moving. And so in my own personal weather station, for example, it's fan aspirated, so it's shielded inside a container that keeps air up inside of the sensor housing during the daytime hours to avoid precisely that issue. So again, apologies that I cut out there. I never see that I cut out until a little bit after it actually happens because there's about a 3 or 4 second lag. So apologies there. Again, if anybody has any ideas, let me know, but I'm not going to spend too much time on it in this conversation today. All right, so I knocked out a few questions, I think, that came up. So let me go back and see now there's more questions in the queue, so I'm going to go back here. All right here. A question from Michael about what explains the stark difference in California coastal temperatures versus inland during this heat wave. Yes, so this is not uncommon for earlier season heat waves in California. When we see big heat waves in May, June, July, they typically get dramatically hot 20 or so miles inland, and then often are unremarkable and maybe not even heat waves at all along the immediate coast. This is because the influence of the marine layer usually during most early season or the first half of the warm season heat waves is very persistent, and so you get this really the reason why that's possible or more common in the first half of the warm season versus the second half is because you have in the autumn during those heat waves that tend to make it all the way to the coast, you preferentially tend to have offshore flow, so land to sea breezes that blow essentially that hot air all the way to the beaches and sometimes even out over the open ocean. So in those autumn heat waves with offshore flow, you can get temperatures, the Farallon Islands that get into the 90s, even though the water temperature there is sometimes only 50 degrees Fahrenheit. So that's hard to do, but you can do it if you have a strong enough offshore flow. That tends to happen in the autumn because that's when the interior Great Basin region, the higher elevation plateau essentially, has already started to cool off, which favors the formation of early season surface high pressure systems which set up an offshore pressure gradient. So essentially winds blow from land to sea, from east to west or northeast to southwest, something like that, and keep the marine influence at bay. Whereas in early season, it's still really hot across the Great Basin. You actually more often have a thermal low pressure system across the interior, and that favors the immediate coast at least to have winds that go from sea to land, so a sea breeze from west to east. That keeps things cool along the coast in the early season. That starts to reverse itself later in August into September. And that is why the warmest months of the year along the central and northern California coast are often September and sometimes even October. So it's not when the sun is highest in the sky, it's not when most places experience their warmest temperatures of the year, but it is when San Francisco and Santa Barbara and the North Coast experience their warmest temperatures of the year, almost without exception, precisely for this reason. So essentially, the marine layer is just too dominant early in the season, and there's really nothing to knock it away. Later in the season, though, in the autumn, there often is a mechanism to disrupt the marine layer and to bring that hot air all the way to the coast. Yeah, a couple folks mentioning that there was some brief light precipitation in parts of Southern California yesterday. That's essentially associated with an early, not really early anymore, but a weak monsoonal surge. It didn't really bring anything significant, but definitely some novelty raindrops, if you will, and maybe a bit more than that in a few spots. There wasn't any significant amount of lightning, so I don't think it really caused any problems. Just increased the humidity and brought some mainly sprinkles to some areas. That could definitely happen again at periods in the next week or so. The circulation pattern will be favorable as we sort of get a low-grade monsoon going over the interior southwest, and anomalously strong high pressure remains anchored over the desert southwest and the southern two-thirds or southern half or so of California. And so as that happens, we'll see spokes of sort of vorticity pinwheeling around this broad high pressure system from southeast to northwest. A few of them might make their way over California. There might be some mid-level moisture associated with them, and so additional interesting mid and upper level clouds possible. And if you get really lucky, maybe some sprinkles. If we get really unlucky, perhaps some lightning at lower elevation places. These are always hard to predict, but it's generally the kind of pattern that favors it, even though there's nothing imminently in the forecast right now. As things have dried out a lot in California, that becomes a little bit more of a concern, especially at lower to medium elevations where lightning strikes, even associated with a little bit of precipitation, they don't necessarily need to be dry strikes to potentially ignite fires in places where things have really dried out, as they have below about 4,000 or 5,000 feet. Above about 4,000 or 5,000 feet, things are still unusually moist for the time of year, and at very high elevations, things are exceptionally moist for the time of year. So again, there's going to be this strong elevational gradient, I think, for the rest of fire season, which is really heating up now at lower elevations and elsewhere in the west, but not so much up above 4,000 or 5,000 feet yet. And really above 5,000 or 6,000 feet, it really might not get going much at all this year. So there's an extended window to do some prescribed burning, put some good fire on the ground in a lot of places this year, even in some lower elevation spots, especially north-facing slopes where things are still a little bit moister than elsewhere. So silver lining to that this year for sure. And historically slow start. I should correct that. Not a historically slow start to the fire season, but a more historically typical start to the fire season in California, which is to say there really haven't been a lot of large or destructive fires as of mid-July, which is the way things historically were most of the time. It's only recently we've started seeing these really big destructive fires more frequently early in the season. Typically this was something that happened later in the season, August and September and sometimes into October during these wind-driven events in particular. So the peak of fire season is likely still to come, and don't get too lured into too false a sense of security based on the slow start. It's really picking up across the Pacific Northwest and the interior west over the past week or so. Certainly in Canada, we've been seeing record-breaking season, just breaking. I mean, there are no Canadian wildfire records that I'm aware of that haven't been broken or shattered this year. It's just been an incredible season up there. And the amazing thing, I think the more amazing thing, is it's not been isolated to one or two provinces, but it's been pretty much countrywide, different regions at different times, but there's just sort of this alternating pattern of extreme wildfire conditions, west versus central versus east, and now also increasingly in the Arctic, where places in northern Alaska, even along the Arctic Ocean coast and along Baffin Bay, have seen record-breaking warmth and wildfires as well. So I'm going to take a look here, what questions have come in the meantime. There's some good questions here sort of on the biogeochemistry side, and to be clear, I'm not a biogeochemist, so I might bring in someone who is for a future conversation, but for now I might defer those to later. Folks talking about deoxygenation of the ocean, specific species that are in trouble. One thing that is clear, by the way, is that some of the extremely warm ocean temperatures in the Gulf of Mexico, there has been a mass coral bleaching event off the coast of Florida and probably in adjacent regions as well. So that's probably going to be a bigger story moving forward as those extremely warm ocean temperatures there, especially in the shallow coastal shelves, continues. And of course, for the corals, they can survive a couple of really warm days, but not weeks to months of them, and so it's the cumulative stress that really gets to them. I think that'll be a bigger story later this year. A reflection from Toby that overnight humidity recovery to greater than 30%, I'm guessing that is what that means, even in the recent heat. Yes, and this sort of relates to what I was talking about earlier, is this is largely a legacy of the wet winter and the cool spring that we had. There's still more soil moisture up there than in many recent years, and this is an illustration of how much the long-term trend has mattered in terms of vegetation moisture, soil moisture, and how that relates to things like overnight minimum relative humidity recovery. It's been much better this year than in recent years. There have been some years where overnight minimum temperatures have not really dropped that much, and overnight minimum humidities have not really come up that much. And that has been a really major effect a major factor in why wildfires and why our ability to manage them has gotten much harder, essentially, or we're not managing them as well. And there was a big study in Nature, actually, that came out last year, and some of my colleagues looked at this quantitatively and found that indeed across much of the American West, there's been this dramatic increase in nighttime wildfire activity in recent decades, mainly because of these very strong trends towards decreased overnight minimum humidity recoveries and warmer overnight temperatures. In other words, the night times are getting warmer and you're not getting relative humidities that rise as high as they used to. That used to aid in fires, for example, at night, laying down, as it said, becoming less active, becoming much safer to approach in most cases, not always of course, but in many cases because temperatures are lower, humidities are higher, and often in the absence of unusual weather conditions, winds are also lower in the middle of the night because a lot of diurnal winds, not everywhere, there's some drainage winds that actually sort of occur during the nighttime part of the diurnal cycle, but in many cases those upslope winds that are stronger and in a lot of cases more dangerous because they're occurring during the daytime when temperatures are higher and humidity is lower, that used to allow for firefighters to approach these fires, put in hand lines, sometimes during the not as much in recent years that has inhibited our ability to manage these fires. This year is a good example of a period when this is actually temporarily reprieved from that, where we're getting better overnight humidity recoveries. Temperatures are still staying relatively warm in some places at night, not so much in other places. There's been a bit of this is more of a coastal versus inland thing in California. But what is clear is that the overnight humidity recoveries have been much better this year in most places. It's definitely one of those things where we'll take the wins when they come, and that is one of them this year. So overall, I think the improved overnight minimum humidity recoveries this year are a good thing. They may not make for the best sleeping weather during heat waves, but it does have other benefits for sure. All right, continuing to go down the list. Now there's probably more questions than I can get to in the remaining 20 minutes or so I'll do my best. Let's see here. There's a question from Puma Mountain Lion 777 about whether ocean temperatures, lower ocean temperatures, so I think this means ocean water at depth, get colder during El Nino events, since the upwelling stops heat transferring from the surface to the bottom. This is an interesting question. In places where El Nino inhibits upwelling, like for example off the coast of Peru, something like that, it would result in eventually at some depth level some relative cooling, but of course because you're not moving as much heat from the surface down to depth in that location. But overall, the function of El Nino in the climate system is to release a lot of heat that's stored by the ocean into the global atmosphere, where it dissipates by radiating out to space, but first, a lot of the times, by making its way from the tropics to the Arctic via storms and weather circulation. So fundamentally, El Nino sort of releases this heat that's temporarily stored in the ocean. La Niña actually accumulates heat. So it's kind of funny that we experience La Niña events as cooler temperatures in many places globally, and El Nino as warmer temperatures globally. But in terms of what it does to the heat in the system, it's actually doing the opposite. So when it feels relatively cool in the global atmosphere, well, that's because a lot of the energy that's otherwise coming into the system is instead getting sequestered by the oceans. And during La Niña, it gets sequestered in the western tropical Pacific and also at depth, because there's increased. Another gap in the communications there. Whereas in El Nino, it's essentially the opposite. I would be curious to know, by the way, during these times when I'm mentioning gaps, is it actually coming through on your end as an interruption, or is that just some weird bug that I'm seeing on my end? Based on last time, I'm guessing it's not a weird bug, but it might be helpful to clarify that. So essentially, I think that the answer to that question is, in a limited sense, localized sense, yes. But of course, that doesn't result in long-term warming because it reverses itself during La Niña. One of the interesting things, though, is that because the Earth's climate system is non-stationary and the Earth is absorbing a greater fraction of the outgoing long-wave radiation, That's because of the increasing strength of the greenhouse effect, which brings about human-caused climate change. Each time we have an El Nino event, it's able to, or I should reverse this, each time we have a La Nina event, it's able to store more and more, incrementally more energy in the oceans, and then El Nino events are able to come along and release, if you will, increasingly large amounts of energy into the global climate system. So even though El Nino and La Nina are still not resulting in net long-term increases or decreases in oceanic heat storage, because there's periods where it increases and periods where it decreases, those pulses are getting bigger over time because the amount of energy that's available to be stored by the oceans because of the accumulated energy in the climate system due to global warming, each of those increments is increasing over time. So even an El Nino of similar strength might produce more global temperature increase than you would otherwise expect. Perhaps that's not phrased the best way, but I did want to get that across. All right, a question from Jack Lee. Do scientists have a sense of whether any bigger, maybe broader climate patterns are influencing all these heat waves around the world? Well, yes and no, right? Because, as I mentioned in the beginning, why are so many places experiencing record-breaking heat right now? Well, the main reason is global warming, because what has changed is the baseline temperature of the Earth. El Nino is not new. We didn't used to break all of these temperatures every time we had an El Nino event, and also in many of the mid-latitude regions currently experiencing record-breaking heat, El Nino doesn't particularly increase the odds of extreme heat waves. In some cases, the opposite. So El Nino is a player certainly in the tropics and in the subtropics in some regions, and maybe indirectly elsewhere, but the main thing that's going on is global warming. Now, why are specific regions so much hotter than others right now and are so much hotter than their previous records? That is an interesting question, and it's not always obvious in the moment what's happening. I did mention that emerging theory regarding persistent summertime weather patterns in the northern hemisphere. Again, it's not totally settled science, but there is a growing amount of evidence suggesting that we are seeing an increasing propensity for persistent high-pressure systems and then therefore concurrent extreme heat waves in different areas continentally in the summer months with a warming climate that may be due to the shifting position and strength of the global jet streams in summer specifically. This probably doesn't explain changes that are happening at other times of year, but it might explain some of what we're seeing in the summer months. That's part of what's happening and also connected to global warming, but it's sort of an indirect connection rather than just the rising floor makes everything hotter analogy. This is kind of in addition to that. There are also probably natural climate patterns at play, certainly beyond El Nino, that are a little bit harder to recognize, except in retrospect. It is possible that again, as I mentioned this before, that the after effects of that really unusual volcanic eruption from last year, the Hungatonga eruption in the South Pacific, which injected a record-breaking amount of water into the stratosphere, which we haven't seen before in contemporary modern times, which probably is exerting at least an additional incremental warming effect this year and last year. Again, it's not very large in the scheme of things. It's maybe on the order of like 0.05 degrees centigrade, but that's the global average. And we know that when you put a pulse of something up into the atmosphere in one place, that doesn't have globally symmetric effects. So it is conceivable that that 0.05 increment of temporary global warming from that volcanic eruption this year is manifesting as much more than 0.05 degrees in a few regions locally and essentially zero everywhere else. That's possible. I don't think we understand the spatial pattern of warming from that volcanic eruption that much yet, but it's plausible. I mean, 0.05 degrees doesn't sound like a lot, but in terms of atmospheric circulation, that we don't fully understand yet. So I would say that right now, sort of in order of magnitude of influence, the number one thing is climate change. It really does explain, a majority of the record-breakingness of temperatures globally right now. Secondarily, and more so, maybe even tied with global warming in some tropical and subtropical regions, is the influence of El Nino. And then this more of a wild card, but probably relevant in some places that I don't totally have a good handle on. Maybe the tertiary indirect influences from this huge, weirdly temporarily planet warming volcanic eruption from a couple of years ago. So there's some weird things going on, and then of course there is random variability. Sometimes big extremes happen largely by chance in the atmosphere, just due to random combinations of coincidences in highly complex nonlinear dynamical system, which is our coupled ocean atmosphere, biosphere, etc. So that's maybe the next most important thing, is just randomness is in there as well. So that's sort of what's going on, big picture wise. The explanation for why this year is so much warmer than in recent years is a little bit more interesting and less clear, but the reason why this year is, the warmest year on record globally, and so much warmer than anything we observed in the 20th century, well, that pretty much comes down to climate change. That's what's going on there. Let's see here. So a question from Eric, the implications of the Arctic sea ice decline, or the Antarctic sea ice decline, sorry. Well, obviously not my typical wheelhouse, different hemisphere at a different latitude, but I will reflect on it a little bit, since I am familiar with it. Antarctic sea ice is a bit of a weird thing in that until somewhat recently it was not decreasing. In fact, it was slightly increasing until the last 5 years or so, despite the fact that the climate, of course, is warming. Arctic sea ice was dramatically decreasing for decades now. It's on a pattern that's clearly linked to climate change, but it wasn't totally clear what was happening with Antarctic sea ice. Again, sea ice is different than land ice. Sea ice melting does not raise sea level directly because it's already floating ice, like ice cubes in a glass of water. But it is important, of course, for other reasons, certainly for the local ecology, and for in the Arctic at least, for local communities. It also affects the what's known as the albedo of the Arctic, so the reflectivity, the amount of incident solar radiation that gets absorbed at the surface versus reflected. And you can imagine that an ice-covered ocean reflects a lot more incoming solar energy than a dark, absorbent ocean, even if that water is very cold. In fact, the same ocean can be largely the same temperature as slushy ice, but have very different reflectivity. So even if the temperature of the surface is roughly the same, right around, the freezing point of salt water is a little bit lower than of fresh water, so right around 30 to 31 degrees Fahrenheit. In that case, at 31 degrees, you can kind of be either ice or open water, depending on salinity and other things. But even if you imagine it's exactly 31 degrees either way, you're going to get a lot more absorption of solar radiation if it's open water and you've gone through that phase change from solid to liquid than if it's reflective ice. This is one thing that's going on in the Earth's high latitudes, which answers another question that's nearby, which is, why is the Arctic warming so much faster than the rest of the world? Well, partly it's because of this albedo effect, where you melt more of the ice, you're able to progressively absorb relatively more sunlight than you used to be, and that is a self-reinforcing vicious cycle feedback, if you will. It doesn't explain everything. There's also things that have to do with the vertical temperature structure of the atmosphere and global heat transport, but as it turns out, all of these things are additive, and in some cases multiplicative, and have overall yielded an Arctic that is warming around 3 times faster than the rest of the world. The Antarctic, though, is not doing the same thing, and that's really for 2 reasons. One is that the South Pole, for example, is essentially a vast, high elevation, huge chunk of ice. The North Pole is really the middle of a frozen ocean that increasingly is not frozen anymore during the peak of the warm season. So the geography is very different. The North Pole is in the middle of an ocean basin. The South Pole is at the middle of a gigantic mountain of ice. So effectively land, massive amounts of ice atop land. So, and also the geography of the southern hemisphere is very different. And in particular, there is a contiguous band of ocean in the southern hemisphere surrounding Antarctica. So there are no continents that connect geographically or land bridge-wise with Antarctica at this phase in Earth's history. Antarctica is an island of ice surrounded by liquid water. That means that the Arctic is not like this. The Arctic Ocean is essentially the opposite of that, which is a big basin, an ocean, increasingly seasonally ice-free in many areas. All a nearly enclosed ocean basin, not fully. There's the Bering Strait, and then there's multiple openings east between North America and Greenland and Europe, of course. But it is not a totally enclosed sea. But the Arctic Ocean is more of an enclosed basin. It's not open on all sides. Whereas the southern hemisphere, there's this contiguous band of global oceans, and so also the southern hemisphere just has a lot more ocean in general. Most of the land in the world is in the northern hemisphere, and most of the ocean in the world is in the southern hemisphere. The southern hemisphere is the water hemisphere. What that means is that the jet stream and storm tracks are a lot more linear. They don't have as many disruptions from mountain ranges from orography or from continents as you do in the northern hemisphere. Those jet streams just flow largely unimpeded across most of the southern hemisphere. Really, the only substantive barrier, and it's still a narrow one that doesn't extend all the way south, are the Andes Mountains. All the other mountains in the southern hemisphere are not that tall relative to the jet stream. Australia and the rest of South America and the southern tip of Africa don't really have huge mountains in the same way that the Western North America does with the Rockies, that Europe does with the Alps, and then moving eastward into Eurasia, the Himalayas, and the mountains in eastern Russia and Kamchatka as well. So the geography, interesting geography lesson, I guess. But what I'm really getting at is that the atmospheric circulation of the northern hemisphere is very different from that of the southern hemisphere. The northern hemisphere jet stream is very wavy and undulating. The southern hemisphere jet stream is more sort of like a belt, more closer to its idealized aquaplanet sense. And for this reason, trends in sea ice have been weird in the southern hemisphere because it's harder for warming to penetrate that belt of jet stream winds, particularly because Antarctica is this massive continent of ice. Also, southern hemisphere and the South Pole in particular is the epicenter of the ozone hole. So getting way far afield now, but there are different dynamics in the southern hemisphere. Things have evolved very differently. It wasn't entirely clear why Antarctic sea ice wasn't decreasing / was maybe even slightly increasing for a little while. It could be due to things not related to human-caused climate change. In fact, that was generally the consensus. The Antarctic is kind of protected in some ways from climate change in the atmospheric sense more than the northern hemisphere Arctic is, because it has that circumglobal belt of high jet stream winds, and also because there are other things going on that are important, like the climate change, the regionalized climate change from the ozone hole, which was almost entirely a southern hemisphere thing, and in particular an Antarctic thing. All of these things may have acted to artificially boost Antarctic sea ice for a few decades. Well, it does appear that's over. This year, record-shattering low level of Antarctic sea ice, as of course we're now nearing the peak of southern hemisphere winter. It is polar night in the Antarctic currently, and yet sea ice is not really expanding. It's not because the atmospheric temperatures are not necessarily that cold, but it's a combination of the ocean temperatures being warm and of wind conditions being unusually choppy. So it's hard for ice to form if the water is warmer than usual and it's windier than usual. So that warming ocean is hugely consequential in the long run for continental ice sheet loss, especially with those marine terminating glaciers we hear about so much. The ice sheets in West Antarctica, that's a story for another day. But the point is, the Antarctic sea ice is doing something very different in the last few years, and this year in particularly, where it's the little mean change or slight increases have dramatically reversed into enormous relative sea ice losses. This year is just completely blowing past the lowest level of sea ice ever observed this time of year in the Antarctic. What exactly is going on? I don't think anybody has a good specific explanation for this year in particular. but it will be interesting to see what happens moving forward, because clearly something very anomalous is happening this year in the Antarctic that we don't fully understand yet. Could it be a very extreme manifestation of natural variability? I suppose, but there's probably something else going on here, so it'll be interesting to see how that evolves. I guess you got a bit more of a geography lesson than I was planning on with that one, but hopefully it was worthwhile. All right, I'm going to quickly look through the remaining questions. The hour's up, but I do want to answer maybe one more before I go, so I'm just going to try and choose one from the remainder. Let's see here. All right, there's a question from Vegan Cheeseburger. Something that has been asked by a lot of folks, and there's a little bit of misinformation floating around. On the other hand, it's genuinely an important topic and a little bit scary one. The question is, when might we see regular occurrences of wet bulb temperatures that are dangerous for people to continue living in regions of the U.S., or I might extend that to in specific regions globally, or have we already started seeing this? So the reason I say that, so first of all, what is wet bulb temperature? Well, technically, it's the temperature to which a thermometer will cool if you wrap it in a moist cloth and sling it around above your head. Literally, that is how it's measured manually. There are, of course, automated instruments to do this now, but in some cases, that is actually how it's done. And the reason why, what it's actually measuring, is essentially the degree to which the evaporation of water, which happens as you sling this around from the moist cloth surrounding the thermometer, can cool a surface. And so it's, in many cases, a very relevant variable for humans' ability to withstand heat, because how do humans physiologically cool themselves? We don't have alternative cooling mechanisms like dogs, say, who pant. We sweat from the surface of our skin. That's not universally true it's universally true among humans, hopefully, but not among all animals. So this is one of several internal cooling mechanisms of Earth. But because humans, this is the mechanism that our bodies use primarily, which is to say we sweat and we rely on the evaporation of that water from the surface of our skin to cool ourselves and to maintain equilibrium temperatures. If, for example, the combination of heat and humidity is such that the evaporation rates decrease, because if it's very humid, the gradient in the differential between the humidity and that layer of air, the boundary layer just above the surface of your skin and the ambient atmosphere is less, and so rates of evaporation decrease, the wet bulb temperature therefore increases. So the higher the wet bulb temperature, in practical terms, the less the human body has the ability to cool itself and via sweating and to maintain a safe temperature. There is a theoretical maximum wet bulb temperature at which human bodies, even if you are essentially wearing no clothing and sitting in the shade, where you will eventually and have unlimited access to drinking water, where your body will essentially overheat like a bad battery or a car engine, and your body systems will start to shut down. So essentially there is a wet bulb temperature that is lethal to humans, even if you are completely standing still in the shade with adequate drinking water. That's a scary thought, and it's thought to be around 95 degrees Fahrenheit. That was sort of what the original study suggested. So a wet bulb temperature of 95 degrees Fahrenheit is thought to be potentially lethal to everybody, including very healthy people, otherwise healthy people. Recently, further studies have suggested that temperature is actually a bit lower. It's not 95 degrees, it's more like 90 degrees Fahrenheit, which is still an extremely high combination of humidity and temperature. So you might say, well, we've all experienced, or the vast majority of us, temperatures well in excess of 90 or 95 degrees. Why are we not all dead? Well, we didn't experience those temperatures in the context of extremely high humidities. So we're talking humidities well above 50, 60, 70% in some cases to produce these extremely high wet bulb temperatures. So a humid day, people say that, I was in Florida when the humidity it was 95 degrees and the humidity was 95%. No, you probably were not in Florida when the humidity was that high. 95 degrees, sure, but at 95 degrees, 30 to 40% relative humidity feels extremely humid because the amount of water vapor that the atmosphere can hold at high temperatures goes way, way up. And so you don't actually need a high relative humidity for things to feel sticky. So what I'm getting at, that's what wet bulb temperature is. The misinformation component comes from folks who've been showing maps of what's called the wet bulb globe temperature, which is actually a different metric. That measures the effect of temperature, humidity, but also things like wind speed and ambient radiation. So that's measuring how high essentially is the effective temperature if you are out in the sun working with lots of clothes on in the direct sunlight without access necessarily to water. So it's a different metric. It's a much more conservative metric, and it's not the case wet bulb globe temperatures are inherently lethal. They're still quite dangerous. They can still result in severe and even deadly heat-related illness, but it's not this intrinsic physiologic threshold in the same way that a 90 to 95 degree wet bulb temperature would be. And a lot of folks have been sharing maps of wet bulb globe temperatures showing that much of the central and southern US, as well as most of South Asia, is at or above 90 degree wet bulb globe temperature in recent heat waves. I don't want to reassure folks too much about that because, again, these are still extremely high and dangerous values, but they are distinct from the theoretically lethal wet bulb temperatures that have been discussed in the past. And so that's the reason why we aren't seeing mass casualty events necessarily in all of the cities that have been exposed to those temperatures this year. There has undoubtedly been a lot of heat-related mortality that's gone widely underreported. Usually in extreme heat waves like this, we do count thousands of deaths after the fact in major urban areas in terms of what's called excess mortality. So that's not to diminish the impact of these at all. It's just to point out that when we're talking about true wet bulb temperatures of 90 to 95 degrees, we're talking about an echelon that's even more extreme in most cases than we're currently experiencing. There have been a couple of places along the Persian Gulf this year that have actually truly gotten to wet bulb temperatures in excess of 90 degrees. These are places where there's a lot of air conditioning. So I guess if you're indoors with air conditioning, that is a major mitigating factor, of course. But if you're, again, as I've constantly mentioned, if you work outdoors, if you're a construction worker or a farm laborer, or if you don't have indoor housing, or you just have housing but not access to air conditioning, this is very much a relevant issue. When might we start seeing 90 to 95 degree true wet bulb temperatures in different parts of the world? There is a literature on this. It depends, actually, greatly on the future carbon emissions. I mean, we don't know how much the planet's going to warm. It's largely a social and political question more than a technological or scientific question at this point. So, but could we get there? Yes, absolutely. And will we at least occasionally start to see potentially lethal true wet bulb events in some places in the world, even on a moderate warming trajectory? Say we end up at somewhere between 2 and 3 degrees centigrade of global mean warming, which is sort of our current path. Yes, this is probably something that will happen. Less often in temperate latitudes, although perhaps occasionally in some of the more humid mid-latitude regions. But the biggest concern is in the humid tropics and the humid deep subtropics, and that includes a lot of South Asia. So there are billions of people who live in places in India and adjacent countries especially, but also in parts of equatorial Africa, Southeast Asia, and Central America, and the northern part of South America, that very well could be exposed to large-scale occurrences of lethal wet bulb temperatures, even on a moderate warming trajectory. And that is a fairly sobering thought. It won't be the average state of things. It won't be that hot and that humid on average. But of course, as you can imagine, even temporary or transient excursions into wet bulb temperatures above 90 to 95 degrees Fahrenheit are going to be a huge problem if and when they occur in populated areas, especially in places where there isn't as much societal cooling infrastructure. In other words, in places where there isn't a lot of air conditioning. But even in places where there is, what if there's a power grid failure? What if you don't have air conditioning? And the point is, that could become a potentially deadly problem within hours, not within days, under conditions like that. So even though people who typically do have access to air conditioning, this is one of those situations where your life then starts to depend on it, and I think that's not a place where we really want to be. We're probably going to get there in some places globally, but not everywhere. And interestingly, coastal California is very unlikely to get there to that extent. The places where it could potentially occur in California do include, the people forget about the Imperial Valley in particular in California, which is an agriculturally important region, also a region with low income and less access to cooling than a lot of other parts of the state. It can get extremely hot and extremely humid there. That's the part of the state I would highlight as maybe being at the most risk of this. Not nearly as high as other places on Earth, of course, but within California, that would be the place where I would be most concerned about that happening. And in really higher warming scenarios, perhaps also places like the San Joaquin Valley and the inland valleys of Southern California, but that's a little bit more speculative. So I don't know anybody's done specific research on that, but that's just spitballing a bit from the data we do have. So I've run a bit past, but I think these were good questions, and so I wanted to get to as many of them as possible. I'll do another Ask Me Anything style event later this summer. But for now, thanks for joining. If you do have any additional advice as to what I can do to prevent these drops in the connection, which have really only begun since we moved to a new place and I've set up this office. You may notice that the topographic map is on the opposite side of my head than it used to be. Do let me know. It's not a bandwidth issue. There's very high bandwidth, but it seems that the ISP may still be throttling uploads because there's 2 virtual conversations going on in this household right now via the web. So Xfinity, if anyone works for Xfinity and knows what the heck is going on, please let me know.